I'm David Smith, and he's David Nausbaum, and ours was on audio processing and filtering. So our requirements was we have a PMod mic, which basically it takes in frequencies and makes it an analog signal, then converts it to serial signal, serial 12-bit data for it, and we took that in. We had to take in the signal at a fast enough rate in order to be able to recreate it using the Nyquist rate. We took it in at 20 kilohertz, so the highest pitch frequency is 10K, which is higher than normal speed. I'm probably speaking at 100. We filtered out high-frequency noise, which we seem to have a lot of when we first tried to output the data. And then we send the filtered data to a speaker. We also can stop the data processing with a push button. And if you've ever seen, like on a lot of speakers, they'll have like a little light up for how high the amplitude is, and our LEDs are kind of recreating that by displaying the magnitude. Here's our basic system diagram. Everything uses either the input and the output both use the SPI. Those are from previous labs. We use the timer counter to determine our sampling rate, and we use the same timer counter to output, so it just goes through. And then these are just connected. The filter and the speakers are just connected by wires.
Alright, so pretty much we do this PMod microphone, so this thing is 12 bits, so we have to use an SPI. But what's interesting with it, when we originally started getting data from it, the data was just because this is not a great microphone. We got it for like $25. You don't expect that great of quality. But so what happened? So when we first ran it, like we were getting weird data just because this.
There's a lot of noise.
Yeah, pretty much. So yeah, so pretty much so we use the SPI interface to connect to it, and then we use the DAC to send the signal out. Then we ran it through an analog filter to clean it up, and then we output it to stereo. Then we also output it to an oscilloscope to look at to see the difference between the unfiltered and the filtered. Yeah, so in terms of software, what we had to do is, as you said, we had to come up with a frequency. So pretty much everything runs through up the interrupt handler because you need to get everything in a certain amount of time. Otherwise you come up, the signals come out kind of, you won't be able to go off fast enough pretty much. And so one of the ways to kind of stabilize the signal or make it kind of seem more stable was we average it as like I think every 10 samples or get averaged together and output it, which kind of stabilized what it was coming out because it got rid of a lot of the static, but it's still pretty bad so far. So I guess demo.
For integrating it, we originally were going to use an I2S, but that ended up not being able to work. So we just had it, we ended up building that circuit and just having the speaker directly wired to the output of the filter. The first step in integrating was just get the mic to work. It uses a similar input to the ADC, the analog digital converter. So we started with that base SPI core, and then we had to make some alterations to it just to make it run smoother. Change the sampling rate for fun. The next is testing the filter to see if it works like a filter is supposed to, which I'm glad it did.
Yeah, because that's what is coming out of the DAC. That's after the filter.
So you can, if you zoom in on this, you will see it has like a 26 kilohertz noise, which you couldn't hear, but for some reason it caused the speakers to sound funny, so probably just interference. And then after that, we added LEDs to it, just so you can kind of see the equalizer kind of effect of LED sliding back and forth. And we added our LCD display now displays the magnitude of the frequency as it's going every 5 hertz. How fast is the LCD now?
It's about the same thing as
and so that's our project demo. Oh, and for sound, since the microphone, if we just like talk to it, there'd be a lot of around noise. So we just put a headphone against it so we could hear clearly and get a bigger signal.
You have to be pretty close for you to get any good data. Yeah. So we've tested music on it, and we've actually gotten readable information back.
Yeah, the music comes through. So if you want to do that. Okay, so that was The first thing we did was trying to just get a signal out. So you can get signal generators on your phone, just if you have a smartphone. So this thing is just, it just samples in at a fast enough rate that it can recreate the audio signal. You can also put in something like a square wave, which sounds really ugly. You can't hear it here, but square wave, if you took the E-Lab, if you put in a square wave, it sounds really ugly. But it's because it has a lot of high frequency noise, which is actually being gotten rid of before it gets to the speaker. And then if you want to put in music.
Yeah, and that little pulse or whatever.
That's just actually the phone.
Yeah. It's not.
I don't know what to put on. I'm just going to put this on.
Just put whatever word.
Some people does always get.
I don't know. So there's still a little bit of noise on there, and I think that's from the speaker, because even when we're putting nothing into the speaker, you could hear that noise. So we couldn't get rid of that. I think it actually is part of the speaker.
Yeah. Or just how we're connected to the speaker.
So basically, I guess the purpose of this experiment is you could hold it too.
Yeah, and we can pause it as we specified.
Yeah. So that's our project.
Questions?
Yeah.
So you're